Section 10.2, checking conditions for a multiple regression model, video 2. And I should clarify that the word multiple in the title is in parentheses because in the textbook they omit it. I thought it was important to include it. So in the previous video I kind of hinted that there's a way to get a two-dimensional view of a multi-dimensional scatter plot, which may be difficult if not impossible to draw, depending upon how many dimensions it has. So how do we make this two-dimensional version of a multi-dimensional scatter plot? We create what's called a residuals versus fits plot. In order to pull this off, we have to take every observed collection of values and assign two numbers to it. For example, when we did the printer problem, I believe in an attempt to predict the price of the printer, we were looking at the printing speed, we looked at the cost to print a black and white page, we looked at the cost to print a color page, and I believe we also looked at the time to print a photo. So we had 4 variables. So for every printer, we had 5 measurements. We had 4 explanatory variables: printing speed, speed to print a colored picture, a photograph, cost to print one black and white page, cost to print one color page, and the response variable, the price of the printer. But every printer is a single data point with 5 numbers. So instead of an ordered pair, it would have an ordered quintuple, if you will. So for each data point, which could have who knows how many values depending upon the number of explanatory variables, there are only 2 numbers associated with it in terms of the response variable. There's the response that we observe, and there's the response that we predicted based on the model. So for example, in the printer problem, every printer had a price that we observed, but the model also predicted a price. So since every data point has an observed response value, which is generically called y, and a predicted response value, which technically we should call y hat. Oh, come on, Marker, don't give that on me. I just opened you. Made it. Let's try this one. It's a little bit better. So the predicted value is y hat. We can calculate a residual. And remember that the residual is what you observed minus what you predicted. So the residual is y minus y hat. So for example, in this made-up data set, if data point A, we observed a response value of 25, but we predicted a response value of 24 based on the values of the observed explanatory variables, then the residual would be 25 minus 24, which is 1. And let's just do the rest of them. For data point B, let's say that we observed a response value of 26, but we predicted one of 24. Then the residual would be 2. For the next data point, we observed a response value of 27, but predicted a response value of 28. So 27 minus 28 is -1, meaning that our what we observed was 1 below what we predicted. For the next one, what we observed is what we predicted, so our residual was 0. Our model perfectly predicted the response value. For the next one, 29 minus 27 is 2. And for the last one, 30 minus 31 is -1. So we got all these values, but for each data point, we're going to make an ordered pair. And the ordered pair that we're going to make is the predicted y value with the residual. So for a residuals versus fits plot, for each data point, we plot predicted value, so y hat, comma, residual. So let's make a residuals versus fits plot for this one. Now, because the residuals can always be positive or negative, but generally hover around 0, when we draw this graph, we don't draw it like we normally do with just quadrant 1 where everything is nice and positive. Our predicted values are usually positive, or our residuals can fluctuate between positive and negative. So when we sketch a residuals versus fits plot, we usually draw it about like that. The horizontal axis represents the predicted y-hats, which are also called the fitted y-hats. Hence the name residuals versus fits plot along the lines of line of best fit. And then our residuals are listed along the vertical axis. So we don't need a whole lot of room up and down the vertical axis. We just need to go up and down 1 and 2. We don't even have to go down 2, but we'll just go up 2 and down 2. And then for our predicted y value, or our y-hat axis, these predicted y values only go between 24 and 31. So we'll just start at 24, 25, 26, 27, 28, 29, 30, 31. Now that horizontal line that represents the predicted y value axis is usually called the 0 line because it's where the residual is equal to 0. So again, this horizontal axis is referred to as the 0 line. If a point lands on it, that means its residual was 0, which means that the prediction perfectly matched what we observed. And now we just plot our points, and they're just of the form y hat comma residual. Well, they're right here. So I just have to plot these points. 24 comma 1 would be here. 24 comma 2 would be above it. 28 comma negative 1. 25, 26, 27, 28 would be about here. 28 comma 0 would be right above it. 27 comma 2, or 25, 26, 27 would be up here. And 31 comma negative 1 would be over here. And now we have a two-dimensional representation of a multi-dimensional scatter plot. You would normally never do this by hand. You would resort to technology. Excel does have a way to create a residual versus fits plot, but I'm not going to go through the motions and showing you how to do it, just letting you know it's a thing. So again, a residuals versus fits plot, residuals versus fitted y-hats plot, is a two-dimensional representation of a multi-dimensional scatter plot. By plotting the ordered pairs for each data point, what was the predicted y value based on the regression equation, and what was the residual based on what we observed minus what we predicted. So what is the advantage of a residuals versus fits plot? I'll show you in the next video. Love my cliffhangers.